Number 9, we're given this function. We're asked to find all the critical points of this function. We know that the way we find those is we take the partial with respect to x and the partial with respect to y. My x looks terrible. And then we set both of those equal 0. So partial with respect to x is going to be 2xy squared minus 2x, and then derivative of those are both 0 with respect to x. And now the partial with respect to y, we get 2x squared y. Derivative of that one's going to be 0 minus 2y, and then derivative of 1 will be 0. So I set each of those equal to 0. Set it equal to 0. And the equations that I have to solve then are going to be this one. So what I'll do is I'll just go ahead and factor out. What I see is a 2x will factor out and leave me with a y squared minus 1. And the second one, I'll factor out the 2y, and I'm left with an x squared minus 1. And so I got several different combinations that can cause both of these to be 0. So my critical points are going to be, I can have x equals 0, and the only way then for the bottom to be 0, if x is already 0, this one can't contribute, but y could be 0. So 0, 0 is a critical point. And that's it. That's the only way that I could have x equals 0 in the top. That's the only way to make the top 0 with that combined with the bottom. So moving over here, I know that this is y minus 1, y plus 1. And the same way down here, I didn't quite factor all the way. X minus 1, x plus 1. All right, so same way at the bottom. I could let y equal 0, but then the only combination would be x equals 0, because if y is 0, it can't do anything here to make a y another number. But now I can move over to the y equal 1. If y is 1, I could have the bottom being 0 with, can't have y equal 0, but I could have x equal 1. So y could be 1 and x could be 1, or x and y. And then y could be 1 with x being minus 1. So minus 1 with 1. And then likewise, so that takes care of this one. Y being 1 with each of these possibilities, but then also y could be minus 1 with each of these possibilities. So that'd be a 1 with a minus 1 and a minus 1 with a minus 1. So we get 5 critical points, and then I need to test them. Remember, oh well, we're going to do that below, but that's all we're asked for here with the 5 critical points. Now below, we're asked to test these critical points, and I'm going to go ahead and write my partials, my second partials. That's what I'm going to do. That's what I'm going to need to use. So I'm going to need my second partial with respect to x, which is going to be 2y squared minus 2. I'm going to need my second partial with respect to y, which is going to be 2x squared minus 2. And I need my mixed partial. The mixed partial with respect to y is going to be 4xy. All right, and then like I said down here, it's going to ask me to use the second derivative test to determine whether each of these critical points is a max, min, or a saddle point. And to do that, I need my discriminant, which is why I was multiplying this stuff out. So that's going to be 2y squared minus 2. That's my second partial with respect to x. 2x squared minus 2. That's my second partial with respect to y. Minus the mixed partials times each other, which means it's really the mixed partial squared. Now set up my little table. List my critical points here. They were 0, 0, 1, 1, 1, minus 1, minus 1, 1, and minus 1, minus 1. We had 5 of them. And for each of these, I need to determine whether the discriminant is positive or negative. And anytime the discriminant is positive, I'll need to check my second partial with respect to x, because that will help me distinguish between whether I have what kind of extrema I have. So this will be determining whether I get a local extrema or a saddle point. All right, so here's my discriminant. I'm going to plug in 0, 0. So you can see when I plug in 0, I get a minus 2. Plug in 0, I get a minus 2, so that's going to be 4. And when I plug in 0, I'm going to get 0. So this is going to be greater than 0. It's positive. It says I do have a local extrema. And when I plug this point into my second derivative with respect to x, either one of these is fine. That's the second derivative with respect to x right there, but you could do this one as well. Anyway, plugging in 0, I get a negative from this. So this one is less than 0. And remember, if the second derivative is less than 0, that means you've got concavity that's downward. And concavity that's downward means you have a local maximum. that point. Now plugging in 1, 1, well, this is being squared, so you get 1, so that's going to be 0, so wiping out this first term. Plugging in a 1, 1 here, you get 4, and you're squaring it, so this is going to be negative, which means saddle point. And 1 minus 1, well, since I'm squaring here, in every case, all of these 1s would be squared, whether positive or negative. You can see every single time I'm going to get 0 over here because I'm going to get a 1 squared or a negative 1 squared in either of these spots, so wiping this term out. So it all comes from the second one, and since this will always be squared, this second one's always going to be negative. So you can go through each one if you want. They're going to all be negative, which means I get a saddle for each one of these. So I get 1 maximum and then a bunch of saddle points.